Today we're going to look at complex numbers, which you should be somewhat familiar with. You should have seen them before. And I represents the square root of -1. So for the opener, I'd like you to simplify I to the 47th power. So you should hit pause, work out what you think the answer is, and then go ahead and see how you did. Okay, so first of all, we know that the square root of -1, which sometimes arises in applications like in engineering, so we needed to decide how to do mathematics with it. So we're going to refer to that as I. Kind of like you let 3.14, 15926, etc. Equal pi, or 2.718 is E. So I is reserved for the square root of -1. Now what happens when we want to do I squared? Well, that's the square root of -1 times the square root of -1. And here is where students tend to make a mistake, and they think of the property of square roots with real numbers. And so, for example, if I had the square root of a times the square root of b, and a and b are real numbers, I can combine those and do the square root of a times b. But that's not the case with complex numbers, and so that'll lead to a lot of mistakes. So when we take the square root of -1 times the square root of -1, we're going to wind up getting, the square roots is going to cancel, and we're going to wind up getting -1. Now what happens when we do I cubed? Well, that's I squared times I, and I squared was -1, so we have -1I. So let's get rid of all this and let's start writing our pattern. I squared is -1. I cubed is -I. How about I to the 4th? Well, I to the 4th would be I squared times I squared, which is -1 times -1, which is +1. So I to the 4th is +1. How about I to the 5th? Oh, and by the way, for I to the 4th, you could have said, well, isn't that I to the 3rd times I to the 1st? Sure. What's I to the 3rd? -I. And then I to the 1st. So we have -I times I, which gives us -I squared. And I squared is -1, so we have -1, which is +1. So it doesn't matter how I split it up. I'm just trying to do it the easiest way possible. So let's keep going. What if we did I to the 5th? Well, that's I to the 4th times I. And I to the 4th is 1. And so we have just I. So I to the 5th equals I. Now I'm starting to see a repeating pattern. How about I to the 6th? Well, you can think of it a couple of ways. We could do I to the 5th times I to the 1st, or we could do I to the 4th times I to the 2nd, etc. So I to the 5th is just I, and then times I gives us I squared, which is -1. So I to the 6th is just -1, just like I squared. How about I to the 7th? Well, that's I to the 6th, which is -1, times I, so we get -1I, just like I to the 3rd. And the last one I'll do is I to the 8th. That'll be I to the 7th times I to the 1st, or even easier, how about I to the 4th times I to the 4th? 1 times 1 is 1. So you can see that we're starting to see this repetition. So any multiple of 4, I to a multiple of 4 power, is going to equal 1. So for example, if I said what's I to the 20th, well, that's I to the 4th to the 5th power, and I to the 4th is 1, and 1 to any power is 1. So when our exponent is a multiple of 4, it's going to equal 1. So now we are finally ready to answer the question, what is I to the 47th? Well, let's split that up into a multiple of 4. 4 goes into 40, 4 goes into 44, 4 goes into 48, but 48 is too big. So I'm going to write this as I to the 44th times I to the 3rd. And I to the 44th, since that's a multiple of 4, is just going to equal 1. And I to the 3rd, we've already established, is -I. So we get -I for I to the 47th. And there's the patterns. Okay, so we're going to talk about the complex numbers. And we have a lot going on here. So the standard form for a complex number is a plus bi, where a and b are real numbers. A is called the real part, and bi is called the imaginary part. If b is not equal to 0, then we have an imaginary number. And if b equals 0, we just have a real number. So it's important to understand, a lot of times students think complex numbers means the same as imaginary numbers. So the complex numbers is kind of like an umbrella. It includes the real numbers, which we've been working with, and it also includes the imaginary numbers, and that's when that b value is not 0. So for example, the number 8, which is a real number, we can write that in standard form for complex numbers as 8 plus 0i. All right, so let's do some calculations with complex numbers. Write each of the following in standard form. So remember, standard form means this. It's going to look like a plus bi. So we look at the first one here, and we can break this down to be 8 times negative 1. And the square root of 8 is 2 root 2. And then the square root of negative 1, we just use I for. Now, this doesn't have a 0 in front, but we could write a 0. And if you don't write the 0, it's still okay. It's still considered standard form. Let's try the next one. We have 5 minus the square root of negative 9. So I can think of that as 9 times negative 1. And so we're going to have 5 minus, and the square root of 9 is 3, and the square root of negative 1 is I. So 5 minus 3i. On the next one, we have negative 4i plus 7i squared, but I squared equals negative 1. So we get negative 4i minus 7. Except in standard form, we have to write the real number first, so we're going to write this as negative 7 minus 4i. So a is equal to negative 7, and b is equal to negative 4. All right, so there's some simplification. What if we do some things like multiplication? Well, think of this pretty much as what you have done in algebra with an x instead of an I. So a lot of the same ideas apply. So when I look at this first problem, I have to distribute the 2. So let's do that. We get 16 minus 6i. And then I'll have to distribute that negative, so minus 9 plus 5i. And now we're just going to combine like terms. So 16 minus 9 is 7. And then a negative 6i plus 5i is negative 1i. So 7 minus I is our answer, and that's in standard form. Now, it didn't say to put it in standard form, but the convention is when you're working and simplifying complex numbers to put it in standard form when you're finished. All right, the next one looks familiar, and we just have to remember we need to distribute or FOIL. So I'm going to take this 4 and multiply it by everything in the other parentheses. 4 times 5 is 20, and then 4 times negative 3i is negative 12i. Next I'll do multiply the I times everything in the other parentheses. So I times 5 is 5i, and then I times negative 3i is negative 3i squared. So negative 3i squared, remember I squared is negative 1, so negative 3 times negative 1 is a positive 3, and then I'll add that to the 20 and get 23. And then negative 12i plus 5i is negative 7i. We're done. Okay, same idea in the next one, although you might recognize that it's the difference of 2 squares. And so the middle terms, when you multiply everything out, are going to cancel. But let's write it out anyway. Square root of 3 times square root of 3 is 3. Square root of 3 times negative 4i is negative 4 root 3i. And that's generally the order we write it. I mean, we could write negative 4i root 3, or negative root 3 times 4i. But the way we've always been writing stuff is you write the number in front of the square root first, then the square root, and then put the I after it. Just make sure it doesn't look like I is inside the square root. All right, so now we have to multiply the 4i So 4i times root 3 is a positive 4 root 3i. See, those are going to cancel. And then 4i times negative 4i is negative 16i squared. So those middle terms cancel out, and we get 3 minus 16 times I squared, but I squared is negative 1, so 3 plus 16 is 19. And if you want, you can write plus 0i, but you don't have to. Okay, at this point, I'm going to show you something which maybe I shouldn't, but we'll see what happens. On your calculator, you can actually do some of these operations with imaginary numbers. And if my calculator works, I will show that to you. The first thing you're going to have to do is you need to go to mode on your calculator, and you're probably in real numbers. So you scroll down where it says real, and then you want to move over to complex, which is a plus bi, and press enter. Then you can quit to the home screen. Now, let me work out the first problem. I'm just going to type in 2 parenthesis 8 minus 3, and then the I is above the decimal point on the bottom row. So I'm going to press second and the decimal point to get I. Close parenthesis minus, and then 9 minus 5i. Second decimal point to get my I. Double check that I typed it incorrectly. Looks good. 7 minus I. Well, that was a lot easier. Let's try the third example. Parenthesis. This will really test it. The square root of 3, get outside the square root, plus 4i. Close that off, open up a new set of parentheses. Square root of 3 minus 4i. And boom, 19. Now, sometimes you're going to see what happens on these is you might see like, here, let me write this over here. You might see 19 minus 4e negative 13i. And so what the calculator is saying, oh, it's 19 plus negative 4 times 10 to the negative 13th power times I. What's negative 4 times 10 to the negative 13th? Well, if we move the decimal 13 points to the left, that's a really, really tiny number. It's almost 0. And what happens sometimes in the calculator when it's doing its calculations, it has to do some approximations. And so when you see that, something obnoxious like that, negative 4e to negative 13 or positive 3e, negative 12, that essentially means 0. And so that's what we saw in here. It's 19 plus 0i. So if you ever see that, don't panic or think you have some bizarre answer. It's just a little bit of a rounding error for the calculator. All right, let's look at a few more examples. Oh, by the way, in that third example, we multiplied by two binomials that almost looked the same, except one was a plus and one was a minus. And when that happens, the middle terms cancel out, and you're going to get a squared minus b squared I squared. Should write that over here. A squared plus b squared, a squared minus, you get the difference of two squares, b squared I squared. But I squared is negative 1, so that becomes a squared plus b squared. And those are called complex conjugates. So remember back in Algebra 1 and Algebra 2 when you were told you can't have square roots in the denominator? The same applies here for complex numbers. You don't want to leave I in the denominator. So what we need to do to get rid of that is multiply by a form of 1, and we're going to do the complex conjugate. So 2 plus I, we're going to multiply by 2 minus I. Notice I'm multiplying by a form of 1, and 3 over 2 plus I is just an expression. It's not an equation. For expressions, you can only multiply by forms of 1. Otherwise, you're changing the value of that expression. Now, when you're solving an equation, you can multiply by anything you want, as long as you multiply both sides by that. But here we have to multiply by a form of 1. So now in the numerator, if I distribute the 3, I'll get 6 minus 3i. In the denominator, I'm going to get the difference of 2 squares, so I'll get 4 minus I squared. But I squared is negative 1, So 4 minus a negative 1 is 4 plus 1 is 5. So we have 6 minus 3I over 5. Now that's not in standard form, so we need to split this into two fractions. So we get 6 divided by 5 minus 3 divided by 5 times I. And now we have it in standard form. All right, for the next example, you cannot add fractions unless they have a common denominator. So I'm going to need to multiply the first fraction by the complex conjugate, which happens to be the denominator of the second fraction. So 3 minus 2i over 3 minus 2i. And then the second fraction I'll multiply 3 plus 2i over 3 plus 2i. Well, this works out nice because those are complex conjugates, so I will not get an I in my denominator, so I won't have to worry about fixing that later on. The I's are going to disappear. So when I distribute the 4 in the first one, I'm going to get 12 minus 8I over this common denominator. And then in the second one, I'm going to get a 9 plus 6I. I'm going to go ahead and multiply out that common denominator. And I'm going to get 9 minus 4i squared. And I squared is negative 1, so it's really 9 plus 4, which is 13. In the numerator, let's combine like terms. So the real part's 12 plus 9 is 21. Negative 8i plus 6i is negative 2i. Once again, let's split these into two fractions. So my final answer will be 21 over 13. Minus 2 over 13i. And if you like, you could check that with the calculator and see what happens. Actually, that might be a good one to test. So let's type in the original problem, which was a fraction. 4 divided by parenthesis 3 plus 2i plus 3 divided by parenthesis 3 minus 2i. Let's see how they handle this. Oh gosh, we get all these obnoxious fraction or decimals. But if I press the math key in the first column, and then I choose number 1, which says convert your answer to a fraction, and then press enter again, there's my 21 over 13 minus 2 over 13i. Pretty handy. All right, I'd like to wrap this up with two more examples of solving equations, which are going to involve complex numbers. So in the first problem, in the real number system, we'd say there's no solution, because when I subtract 20 to the other side, x squared cannot equal negative. But now that we're in the complex number system, I take the square root of both. The square root of x squared is the absolute value of x. And the square root of 20, think of that as, or square root of negative 20, think of it as square root of 20 times square root of negative 1. And the square root of 20 I can simplify to 2 root 5. And the square root of negative 1 is I. So therefore, x is going to equal plus or minus 2 root 5 I. Now, if you had actually oh, by the way, we could check that. Let's check it in a different column. If I plug in 2 root 5i for x in my equation, square it and add 20. 2 root 5 times 2 root 5 is 4 times 5 is going to be 20. I squared. And then I squared is negative 1, so that's negative 20 plus 20, which is 0, which is what we're supposed to get. And then if I plug in a negative 2 root 5i, when I square it, it's still going to become positive 20 I squared. And that'll be negative 20 plus 20 is 0. So both of those work. Let's look at one last example here. And then I'll talk about graphing this in the coordinate plane. So the first thing you try and do with a quadratic like this is factor it if possible. And you realize pretty quickly that there's no two numbers that multiply to equal positive 26 and add to equal positive 10. So factoring is not going to help. Well, the method that always works, because factoring doesn't always work, is the quadratic formula. So x is going to equal the opposite of b, which is 10, plus or minus the square root of b squared, which will be 100, minus 4 times a times c, all over 2 times a. So now we can simplify this. Negative 10 plus or minus the square root of 4 times 26, that's 425 is 100, and another 4 is 104. So 100 minus 104 is a negative 4 over 2. Now the square root of negative 4, that's 2i. So we have negative 10 plus or minus 2i over 2. And then we can split that up into two fractions. Negative 10 divided by 2 is negative 5, plus or minus. 2i over 2 reduces down to 1i. And so there's your two solutions. Those are the two zeros of this quadratic in the complex number system. Now before we were dealing with complex numbers, when we were only in the real number system, we would graph this parabola and it would turn out that it's opening upward and the vertex is above the x-axis. Somewhere, I don't know, let's just say it's over here somewhere. And then it's opening upward. So there were no real roots for this particular quadratic. But in the complex number system, we have two roots.